So in yesterday's session, we have understood RF characteristics and RF behavior, how a wave travels in the Wi-Fi space, or how the wireless communication happens. So how an antenna emits the radiation. So these are the concepts that we understood. We understood how a wave behaves, what are the characteristics of the wave, like the frequency, amplitude, phase, and all. We have understood if we tune amplitude, that means what? We are increasing the power, we are increasing the strength of the signal, right? And also the wavelength is inversely proportional to the frequency, so that also we have seen. And then at the last we were talking about the RF components. In the RF components, there will be a transmitter, then an antenna cable, and then the antenna itself. The point where the antenna begins, this is the antenna component. So this is the point where the antenna starts. So at this point, this is the intentional radiator, that is IR. So IR is a terminology. So that includes the transmitter power and the loss on the antenna cable, that is 3 dB loss, 15 dB minus 3 dB. So that is 12 dB. So 12 dB is the intentional radiator, IR. So then we have the EIRP, which is a sum of transmitter power, noise, plus the antenna gain. Okay, antenna gain. So what is the antenna gain? So we will learn in the antenna section, but for now you understand that if the signal is 12 dB here, by using an antenna, you can boost the signal by another 3 dB. So in that case, again, the signal strength will be 15 dB. So when it is emitting the radiation, this is the EIRP, that is, this is the value, that is the transmitter power, noise, plus the antenna gain. So that is all EIRP. So this one we have understood at the end of the session yesterday. So transmission power, cable loss, antenna gain, that's the EIRP. So EIRP is the highest RF signal strength that is transmitted from a particular antenna. And then you can see here, there are some units of measurement. So that is nothing but the power. Okay, power. So we'll talk about this power. So welcome everyone for today's session, and I hope you are doing great today. And this is the third day of our class. In the first session, we have completed the introduction. In the second session, we have completed the RF behavior and characteristics. So today we are learning about the measurements. Okay. So Wi-Fi signal process and the measurement requirements to calculate signal strength and other power related concepts will be covered today. So as a wireless engineer, we must evaluate wireless signals to determine their quality. When the radiation is going out of the antenna, so we should be able to tell the quality of the signal. For understanding this quality of signal, we need to understand the measurements. Okay. So power levels decrease exponentially as they radiate from the transmitter, right? So if you have a AP here in a space, and that AP is going to emit the radiation, and that is nothing but the power. So at certain power level, it is going to emit the radiation, and power is measured in watts. Okay, power is measured in watts. So what exactly the power is? Power is nothing but the energy that you apply over the time. For example, you have a door and you push that door, right? You push that door to close. The amount of energy that you use to push that door in order to close the door, so that is what the power is. Power is the amount of energy applied over the time. Okay, that is what power is. To tell in more technical terms, power is nothing but the voltage that you apply and the current that you generate, that is voltage into current, that is power. Okay, V into I. For example, if you remember the first class, we just applied a voltage of 1 volt sorry, we applied a voltage of 1 volt to a battery, and that was able to generate a charge of 1 ampere. That was able to generate one charge, and it traveled from negative to positive. So that action generated 1 ampere of current, right? That voltage and the current, that is what the power is. And power is measured in terms of watts. Okay, this is the actual measurement of power. So what is a power? Power is energy applied over a period of time. So that is what power is. So in terms of our radiation that is getting emitted from the antenna, suppose you have this antenna and you are emitting the radiation out of this antenna. So what is the power level at this point? What is the power level when it is away from this point? So we need to calculate this as a wireless engineer. We should know, when I say when the power at the antenna, it is 15 dB. Okay. But we know that since the radiation is going all around in the 360-degree direction, as it moves maybe a meter away or a 1 feet away, so the signal strength or the power will decrease exponentially. So it will decrease in such an extent, maybe it will come as a zero point 0.1 or 1 dB, or it can go into minus values as well, like minus 30 dB. So as you move a little bit ahead of this antenna, so the power will be decreasing in exponential way. Okay, so power is nothing but voltage into current in a technical terms. But in a layman's language, what is a power? Power is an energy that you apply in order to achieve some task. For example, you take this circuit, you apply a voltage of 1 volt and it generates a 1 ampere of current. So the total is called as power, and this power is measured in watts. Okay, and yeah, so and the unit of measurement is watts. For Wi-Fi space, we are going to use, like, the APs will be giving the power, or the radiation would be emitted, that is 10 milliwatts, between 10 milliwatts to 100 milliwatts. Okay, so the AP can generate the power and send that is 10 milliwatts to 100 milliwatts. Suppose if you want to send the signal to far distances, what is the criteria or what is the parameter that you are going to change? If the signal wants to travel longer distances, so then you are going to increase the power. Okay, you're going to increase the power. When you increase the power, the signal is going to travel for longer distances, but it is prone to attenuations from the external world. Like, it can be some obstacle. There is, if it is an outdoor transmission, so then obviously the buildings and the trees, so these all things can lead to the attenuation of the signal. So obviously when you send the signal to in a longer distances, so then you will have attenuation, more attenuation. And we know that as the signal strength will decrease with the distance due to the free space path loss as well, that we explained yesterday, free space path loss. Just like a person putting a hand into a pond and the ripples get created. So those ripples get weaker as they move away from that finger, right? So that is the one analogy. So basically, if you want to enlarge the cell size of an AP, so then what are you going to increase? We are going to increase the power. Okay. A higher power indicates more energy applied in the less time. So that's what power is. And power is measured in watts. A watt is a basic unit of power. 1 watt is equal to 1 ampere current flowing at 1 volt. Okay, so that's what in technical terms. In a layman terms, the energy, the push that you give to this door in order to close that door, so that is what power is. Okay, as a wireless engineer, so you need to understand what will be the power at the antenna. If it moves some distance from the antenna, what will be the power? And if you cut down the power by half, okay, so the distance also is cut down to half the power cell size. If you double the distance, so if you double the power, so how much distance it is going to cover? So that is what we are going to learn in this section. Normally, for the Wi-Fi communication, we use power. We use the unit of power as milliwatt. A milliwatt, a milli is nothing but one divided by 1000 of watts. Okay. In 802.11 wireless transmission, so this is the standard for the wireless communication 802.11. We would be transmitting signals between 1 milliwatt to 100 milliwatt. Okay, it is not 10. Okay, so it is 1 milliwatt to 100 milliwatts. And there is one more measurement that is being used in the Wi-Fi space, that is decibel. This is also used in sound, right? But in Wi-Fi also we use dB. So it is a unit of comparison and it is not the actual unit. So milliwatt is and the milliwatt and the watt is the actual power unit of power. But decibel is not a unit of power, it is a unit of comparison. Okay, comparison, not a unit of power. It is used to represent a difference between two values. Decibels are often used either to compare the power of two transmitters or more often to compare the difference or loss between the EIRP output and the amount of power received by the receiver's antenna. So now let's try to understand the decibels. So we know now that watt is the measurement value for power. And in Wi-Fi space, we are using milliwatts. And there's one more terminology, that is decibel. Okay, decibel. And this decibel is not exactly the unit of power, but it is the relative or the unit of comparison. Okay, why it is unit of comparison and all, I will explain. So decibel, deci. So I was explaining about the decibel. So decibel is nothing but deci means 1/10. Okay, bell is the great scientist Graham Bell, right, who invented the phone. So deci is 1/10 and Bell is Alexander Graham Bell. Commonly, decibel is commonly used for measuring sound and wireless signal strength. So understanding the decibel involves basic knowledge of logarithms. You should know something called as logarithms. But as a wireless engineer, so it is not like you need to know the hardcore mathematics of this, but in a high level, I will just explain you. So logarithm help convert exponential changes into a linear scale. So that's what the logarithm function does. But why we are talking about this? So we have a signal. Suppose say you provide a signal of 100 watts. When I say a signal of 100 watts, that means you need to imagine this picture. There is an antenna. I am going to provide a signal that is having a strength of 100 watts, which is not possible in Wi-Fi communication because the signals are between 1 milliwatts to 100 milliwatts. But for just explaining purpose, I am just taking this value. Suppose you imagine an antenna sending a radiation on 100 watts. Okay, at 100 watts. So it is easy for us to calculate. Suppose if it goes a few distance away from the antenna, so since it is traveling in 360-degree direction, 360 degree space, right? So the radiation is not like a user is sitting here, a user is sitting here, and the AP is not going to send a sine wave to him and one more sine wave to him. The radiation travels in 360-degree direction like this, in all way like this. Okay, it will travel like this. Just imagine the person putting a hand into the pond, right? So it will create a ripples in 360-degree. So similar way, the waves will travel in the atmosphere. So now when it is traveling in 360-degree directions, so that's why the power will decrease exponentially. Now it is 100 watts, maybe it comes down to 50 watts here at this point. So if it moves little bit further, maybe it comes to like 1 milliwatt. Then it goes from 1 milliwatt to 1 milliwatt to maybe say zero point 0.5 milliwatt. Sorry. So 1 milliwatt, and then it will go to maybe zero point 0.1 milliwatt. And if it goes little bit far away, then it goes to 0.001 milliwatt. Okay. So now instead of going as like 100 watts, 50 watts, and then it is going to very low numbers, right? Like 1 milliwatt and zero point 0.1 milliwatt. So for ease of our in Wi-Fi space, we are using the signals between 1 milliwatt to 100 milliwatt. Why? Because the signal, the power that we are sending is very, very low. If I want to indicate this 1 milliwatt in a watt, that means 1 watt is equal to 1000, one divided by 1000. So this is the value that I will get. That is nothing but 10 to the power of minus 3, right? So that is what the milliwatt you need to mention. That is 0.001 watt. So if the signal is going like this, 100 watts, 50 watts, or suppose it goes to 1 watt, that is it is going to 0.001 watt. Then it is going to 0.00001 watt. Instead of me telling like this, so what I will do is I can tell it as 100 milliwatt. So that is why we are changing it from watts to milliwatts. The reason why we are changing it is as the distance increases, as the radiation is passing, so the signal will decrease exponentially. So if it is 100 watt here, so it will be 50 watt at this point. So if it travels maybe one feet away, so then it might be like 25 watts. And then it will be maybe 1 watt, then 0.1 watt, 0.01 watt, 0.001 watt. So this is not easily you can understand, or it is not human readable, right? So that is the reason for um, to have a better value. So we convert this from watt to a milliwatt. Okay. So that is the reason we are going to convert it, and how the conversion will happen. So let's see that now. There's an option to clear the text. Where is that? So now we understood that Wi-Fi space, we are going to communicate with 1 milliwatt to 100 milliwatt. So it is not even in watts. And since it is such a small value, we need to represent watts into milliwatts. Suppose you take 1 watt. This is equal to 1000 milliwatts. Okay. Similarly, if you take 10 watts, it will be 10,000 milliwatts. If you go to a smaller watt, for example, 0.1 watt, so it will be 100 milliwatts. Similarly, if you go for 0.5 watts, it is 50 milliwatts. So how are we arriving at these values? So that is, we have a rule, that is metric conversion, that says if it is 1 watt is equal to 1000 milliwatts, or 1 watt is equal to 1 divided by 1000. Okay, 3 zeros is milli. Okay, 1 divided by 1000. So if I say zero point 0.1 watt, right? 0.1 watt, zero point 0.1 into 1000 I need to do. If I do 0.1 into 1000, that is 100 milliwatt. Similarly, if I say 0.5 watts, it should be 0.5 into 1000. So that is 50 milliwatts. If I say 0.025 watts, then 0.025 into 1000, it is 25 milliwatts. So like this, you need to do the conversion between watts and milliwatts. The simple logic is 1 watt is equal to 1 divided by 1000 watts. So that is nothing but 100 milliwatt. Okay, 1 watt is equal to 100 milliwatt. So this is the metric conversion that you can do for a watt to 100 milliwatt. And what is the reason we are changing from 1 watt to milliwatt? Because the signals that we are using, it is having very less power values. Okay, this is 1 milliwatt. If I want to represent the same thing in watts, so how much it will be? If it is a 1 milliwatt in watts, if I want to represent this in watts, suppose this is 1 milliwatt, right? 1 milliwatt is 1000. So that is 1000 means 0.001 watt. So if is it a this one is a better value, or 1 milliwatt is a better value? So 1 milliwatt is a better value. So that's why we choose 1 milliwatt to represent the power. Okay, and these two, either it is a watt or a milliwatt, is a direct unit of measurement, unlike the decibels, which will come next. Okay, so just to summarize, what we have understood till now is we need to convert watts to milliwatts for Wi-Fi communication. The reason for it is the values that are radiated from the antenna are very small. If I want to represent those in the terms of watts, it will be very hard as it is not readable. So this value over here, if I want to represent 0.001 watts, so it will be very hard for doing the calculations. So that is why I will come up with this value, that is milliwatts. So 1 watt is equal to 1 divided by 1000 times. So that is nothing but 1 watt is equal to 0.001, sorry, 1 watt is equal to 1000 milliwatts. Okay, we can say 1000 milliwatts. Similarly, if the signal degrades to 0.1 watt, very small signal. So what you need to do? You need to multiply 0.1 by 1000, then you will arrive at a value that is 100 milliwatts. Similarly, 0.5 watts is equal to 0.5. If you want to represent in milliwatts, 0.5 into 1000. Okay, why? Because 1 watt is equal to 1000 milliwatts. So that's the metric conversion that you have, the base value. You can say 1 watt is equal to 1000 milliwatts. And if you want to convert any watt value, a smaller watt value, so then you need to multiply it by 1000, then you arrive at a milliwatt value. So that's the basic principle. Okay, I hope this till this point it is clear. Okay. Do you want me to repeat? Or is it clear till this point? Conversion from watt to milliwatt. What is the logic for conversion? Is it clear? Okay, perfect. So now once we are good with this, we are converting watt into milliwatt to arrive at a smaller value. Now there is one more thing that is called as decibel. Why we need a decibel? The reason for this is again the power values, that is very small power values. Even the milliwatt is not enough, where milliwatts also will go to like 0.001 milliwatt, 0.0001 milliwatt. So watts is unimaginable in the Wi-Fi space. Milliwatts, like 1 milliwatt to 100 milliwatt, it is the power that is going to go out of the antenna. Okay, that is the range. But we know that the signal is getting transmitted in a 360-degree direction, and the signal strength will decrease exponentially. The signal strength will decrease exponentially. So when it decreases exponentially, like if a antenna is emitting at say 30 milliwatts, right? So that is EIRP value. When I say EIRP value, that is the transmitter power minus the cable loss, okay, the cable loss and the antenna gain. So adding all those things, that is 30 milliwatts. But we know that in a Wi-Fi cell, when the signal is traveling, when the radiation is going out, it is going to decrease its strength by exponentially. Exponentially means if it is 30 milliwatts here, after some time it will be 1 milliwatt. After maybe 5 feet away, it will be 0.01 milliwatt. After that, it will be 0.001 milliwatt. So now you might have question. In the previous example, I told that 1 watt will change to 50 watt, 1 watt, 100 watt power if you are generating. It will also decrease exponentially and it will go down. But that is just for your reference. I told why watt to milliwatt. But in actually in the Wi-Fi space, you are sending the signals between 1 milliwatt to 100 milliwatt. Suppose there is an antenna that is going to send at 30 milliwatts. So the signal strength at the antenna, that is the EIRP, is 30 milliwatts. If the radiation is moving like a 1 feet away, then it is like 1 milliwatt. If a signal is measured here, that is 1 milliwatt. Question for you. So how I am going to measure a signal strength here? Okay, at this point. So what you can do is, a person is sitting with a laptop. He can have applications like NetSpot or any other applications he's having in his laptop, and is connected to this particular SSID. And now when the laptop is moving one feet away, in that NetSpot, you can see the signal strength as 1 milliwatt. Okay, 1 milliwatt. So this is nothing but the RSSI, that is receiver signal strength indicator. So the receiver signal strength indicator, now it is indicating 1 milliwatt. Okay, 1 milliwatt. So if he moves 1 feet away, then it is 0.01 milliwatt. So you can see the exponential decrease in power as the signal travels in the air. Okay, that is the characteristics of the radiation that is going to propagate. So this is the characteristics of the RF waves. And why it is happening? Because the radiation is happening in 360-degree direction. So since this is also not enough for us, the reason why we came from watt to milliwatt is because it is very hard to represent these values. But now again we are stuck with this, where there are very small values here. So how to get rid of these values? So they came up with one more measurement thing that is called as decibel. But this is a relative measurement and not the actual measurement or the actual unit of power. This is the relative measurement. To understand this decibel, so we need to understand the logarithmic function. Okay, logarithmic function. So I will write a chart here. Okay, and I will make you understand what is the use of a decibel or the dB. Suppose we take a chart here. You no need, this is not a rocket science. You can understand it very well. Okay, it is very layman language. So these concepts, if you learn in physics, it is like too much deeper and too much calculations and all you need to prove. So those things are there. But as a wireless engineer, you need to know the concepts behind the scenes. So that is what is required. So that is what we are doing. What is what we need to understand. Why it is like that and how it we arrive to this one. Like I said, 1 watt is equal to 1,000 milliwatts. Why it is like this? Because it is a metric system. So that is how they calculate. This is the reference value. So how we arrive at it? So then you do some calculations and arrive at that. But we don't need that calculations. We just need to understand what is what. Okay. So now to understand the decibels, I'm plotting a graph. Okay, plotting a graph. So this is the X value. This is the Y value. Okay, this is the X value and Y value, and I will write an equation that is Y is equal to 10x. Okay, 10x. Just see this here. When I make X as 1, okay, 10 to the power of 1 is nothing but 10 into 1, that is 10. So what is the Y value now? Y value is, X value is 10. Sorry, Y value, X value is 1, Y value is 10. Okay, this is a Y value. So Y is equal to 10, X is equal to 1 here. Suppose if I make Y is equal to, sorry, X is equal to 2. So what will be the Y value? This is 10 into 10. That is 100. When I make X is equal to 2, Y value changes to 100. When I make X value to 3, 10 into 10 into 10. So this becomes 1000. Okay. So Y is 1000 when X value you change it to 3. So why are we learning this? So we see that there is an exponential change in the power levels, but it is very hard to represent, very hard to digest, very hard to, it is not human readable. So I want to make it a linear value. So how do I make a linear value? The answer is decibel. Okay, answer is decibel. So with this equation, what I'm trying to prove or what I'm trying to make you understand is how a exponential value, exponential decrease can be represented in a linear fashion. Okay, so I took a equation y is equal to 10x and x is nothing but it how many times you need to multiply this 10. Okay, how many times you need to multiply this 10. So if I multiply one time, so the y value will change to 10. If I multiply two times, 10 into 2 or 10 into 10, sorry, so the y value is 100. So you can see this, the y value is increasing exponentially here, but the x value is increasing linearly, like 1, 2, 3. So now come to this graph. In the x-axis, if I keep it 0 here, so y is equal to 10, 0. That is nothing but if you multiply 10 into 0, anything by 0 is 0, right? So y value is 0 when x value is 0. So the dot is here. Now the x value is 1. When the x value is 1, the y value is 10. So I write it down here. This is 10. So now I arrive here. So the next one, x value is 2. That is here. And the y value is 100. So maybe the 100 is here. It's not possible, but Yeah, 100. So x value is 3, that is here. And what is the y value? So y is 1000. So my graph is not enough to represent this, right? So it's going exponentially, it is going now like this. Exponentially, it is going up, it is shooting up, and the graph is not enough to capture that. So now instead of representing it like this, how about I say 1, 2, 3, 4 and all, right? So that will be more appropriate. Instead of writing the actual value, so I can write some comparative values. So to achieve that, you need to use something called as logarithmic function. Okay, log function you need to use. Okay, log function. So that we will understand in the next section. So just to summarize, we understood about the watt. Okay, that's the unit of power. What is the power? Voltage into current. That is nothing but the energy that you need for a push, the energy that you apply for a period of time. So that is what power is. Okay. So at the antenna, what is the power? If you move 1 feet away, what is the power? So that you should calculate. For calculating this, we have milliwatts because the unit, the power that we are emitting from the antenna, that is 1 watt to 100 milliwatt. And why this restriction is there? So that is because of the standards that is provided by a board called as FCC in the global level, and there are regional boards that will regulate these devices to emit the power. So you can emit as much as power you want. You can emit in watts also, but why are you not doing it? Because of these regulations, which we will learn in the like standards section is there. So that time we will learn more about these regulations and IEEE and all. So after that, then the milliwatt is also not enough for us. We are not able to represent these values because these values are very small. So what is the solution for it? So decibel is the solution. So how we are going to use the decibel? So and what is a decibel? Decibel is a relative value, right? So decibel is um, is going to help convert exponential changes into a linear scale. In understanding that, I have given an equation here and make you understand if I am changing a value, a x value, it is changing exponentially. The y is changing exponentially here. Okay, if I change x values, the y value is changing exponentially. Now, how I can make this as a linear graph instead of having an exponential graph because it is going from 10, 100, 1000 and maybe more, right? So now instead of me representing these values like this, so how can I represent in a smaller values or in a more linear fashion? How I can represent this is what we are going to understand in the next section. Till this point, we have understood that if any value, if any value that is a higher value or a very small value, as in our case 0.01, 0.001 milliwatts, if it is a very small value, I need to make it a linear value. So for that, we need to have a function that is called as a log function. Okay. So let me take a new page and make you understand the log function. Till this point, it is clear, right? Mm, I will take that as a S. Okay. So now let's understand what is a logarithmic function. Okay. So logarithmic function, as I said, logarithmic function, it helps express very large values, very large, very large, or you can say very small in our cases, very small numbers in a compact form. Okay, in a compact form. Okay. So how exactly that we can achieve this with a log function? Let's try to understand. So normally in networking, we take log2 function we use in networking. Okay. But here for the power, we use log 10. Okay, log 10. What is log 10? You will understand. So the analogy is why we use a logarithmic function. So now we saw that in a graph, when I change a x value, so y value is changing like y value is changing like anything, right? It is a exponential increase was happening there. But in our Wi-Fi space is what is happening? Exponential decrease is happening, correct? It is exponentially decreasing. The power levels are exponentially decreasing. So I need to represent those values as a linear values. So that is what we will arrive in another 2 to 4 minutes. Okay. Or maybe more than that, but yeah. So log 10. So we have taken a logarithmic function and we are trying to understand what it is. So log 10 of 0. Okay, if I say log 10 of 0, so this value is 0. I take log 10 of 1, so this value is 1. If I say log 10 of 2, so this value is 2. So log 10 of 3, so this value is 3. So what is happening here? 10 to the power of 1, what that means? 10 into 1, that is 10. 10 into 2, 100. 10 into 3, 1000. So now what happens? Instead of me representing 10 into 1, so y value, what it will be the y value? If I without a log function, if I want to represent y value, if x is increasing, y should increase, right? X value is 1, y value is 10. X value is 2, y value is 100. X value is 3, y value is 1000. So now, instead of giving these things, these y values, so what I do is y value, I will make it as 1, y value, I will make it as 2, y value, I will make it as 3. So how this magic is happening? So how it is happening is because of the log function. So instead of me telling that y value is 100, I say y value is 2. That means what? So if I multiply 10 2 times, I will arrive to 100. So how many times I multiply that number I will write instead of writing the actual number. So this is 100 milliwatts. I don't want to represent 100 milliwatts or 100 watts. I want to represent 2. If I multiply 2 into 10, then I will arrive to the actual value. This is a comparative value, or this is a imaginary value, or this is a comparison value. It is not an actual value that you are representing here. Using this value, you will arrive at a actual value. So that's what this log will do. When you use this log function, and why it is like that and all, if I want to talk in a technical term, it is by design. Okay, those are the log calculations and all. But what we are trying to understand is what is what. So that's it. So log 10 of 0 is 0. Log 10 of 1 is 1. Log 10 of 2 is 2. I will take. But actually 10 to the power of 2 is 100. So instead of me representing 100, I will represent as 2, y as 2. So now if I plot the same graph here, I take x value, if I take 1, now I will start from 0. 0 is 0 only, okay? So if I take 1, x as 1, if I take 1, it is 10 into 1 is 10. But instead of 10, I will take it as 1. So I will be here, 1. And now at x value is 2. If I take that as 2, then again the value is 2. Instead of me representing it as 100, I will represent as 2. So the actual value is 100. If I multiply 2 into 10, so that is log 10. Okay, this is the base 10, you will say. So normally in networking, they take base 2, but here for the power calculation in wireless, they take log 10. Log 10 is the common base here, and we need to multiply the x value 2 into 100, 3 into sorry 2 10 into 10, 10 into 10 into 10 3 times. So like that you need to multiply here and you get a y value, but you are not writing the actual y value, but you are writing a comparative value that is 3. Okay, now you represent 2 here. For 3, it is 3. For 4, it is 4. So you will represent like this and it will be in a linear fashion. Okay, it will be in a linear fashion like this. So this linear fashion, so how we can compare this with our calculations? If I take a value, say 0.1 milliwatt, then we need to represent this in decibels. So I take a reference value that is 0 dB. Okay. If I want to represent 0 dB, so I will say 1 milliwatt. And if I want to represent 10 dB, I will say 10 milliwatt. And 20 dB, then it is 100 milliwatt. So why it is like that, I will explain. Okay. But for now, you need to understand that in the previous slide, we understood that if we change the x value, y value is changing exponentially, then we bought one thing that is a logarithmic function. What is a logarithmic function? It helps to express very large or very small numbers in a compact form. So how it does that? Instead of representing actual y values, I will represent the relative values. What that relative value will do? If I take that relative value and multiply by 10, I will get the actual value. So that relative value I will represent in the graph instead of the actual value. So that relative value is only this decibel. So how we can use this logic into our calculations here. So that is what we will see in the next section now. So let me clear this. I know it is, you know, it is little bit tough, but not once you sit and try to understand and follow all the logics that I'm explaining, it will be easy for you. Okay. If you try to refer the books and if you try to do it, try to learn it by itself, it will take a lot of time. But if you, since I am explaining it like this, so it will be easy for you. Okay. So now I made a statement. We can take a reference value that I take, that is 0 dB is equal to 1 milliwatt. Okay. And then 10 dB is equal to 10 milliwatts. And 20 dB, you can say 100 milliwatt. So just remember the graph. If I chose 0 dB, so it is 1 milliwatt. 10 dB, 10 milliwatt. Suppose I take 20 dB, 20 milliwatt. So that is not the case. If that is happening, then we don't have any discussion here. Why? Because 0 dB, 1 milliwatt, 10 dB, 10 milliwatt, 20 dB, 20 milliwatt. Suppose I say 30 dB, 30 milliwatt. So it will not work like that. Okay, it will not work like this. So it is 0 dB, 1 milliwatt. 10 dB, 10 milliwatt. 100 dB, sorry, 20 dB, 100 milliwatt. And why it is like this? So desa means what? Desa is 1/10. Okay, desa is 1/10. So you need to multiply, um, like, for example, if you have this 0 dB, you have increased this by 10 times, right? 0 to 10. So then 1 milliwatt was there and it increased 10x. Okay, this you increased 10 times and your signals, your milliwatt is going to change 10x here. Okay, so how we are arriving it, like 20 dB is 100 milliwatt, 30 dB is 1000 milliwatt. How we are arriving at this value. So that is what we are going to see now. That is, if you take 10 to the power of 1, right? It is 10 milliwatts. 10 to the power of 2, that is 20 uh, 100 milliwatts. So now what happens is you need to multiply, you need to multiply, you need to multiply, uh, just a minute. Yeah. So in this, what happens is when you are converting from 0 dB to milliwatts, okay, 0 dB to milliwatts. So the conversion happens like this: 10 dB, 10 milliwatts. So how we arrive at this? How we arrive at this value? So we arrive at this value, that is 1 into 10 you are going to do. So then you will get a 10 dB. So for 20 dB, so what you need to do is you need to multiply 2 into 10, and then you will get 20 dB here. So why you are getting 20 dB like this? Because desa means what? 1/10. Desa is 1/10, right? So you need to multiply, you need to, um, I think I took it in. So how you need to understand is desa is 1/10. And when you are converting this to milliwatts, suppose if you want to represent 100 milliwatts, okay, 100 milliwatts, 100 milliwatts. Um, think, hmm, just allow me a minute.